All right, this will be the second part of Module 7's lecture. So M7 covers the end of Chapter 7 and the beginning of Chapter 6. So Chapter 6 focuses on uniform circular motion. It also focuses on gravitation, but we are not going to be looking at this. We will focus on sections 6.1 to 6.4. So the equations we'll be using are from your equation sheet, Chapter 6. If you have it with you, go ahead and get that out so you'll know which equations I am selecting from. Okay, we're going to start with a really simple problem just to begin thinking about circular motion. So how fast does a car tire spin? We're going to calculate the angular velocity of a 0.3 meter radius car tire when the car travels at 15 meters per second. Okay, so we have the angular velocity here. And the symbol for angular velocity is this omega sign. This stands for angular velocity, and that is what we are looking for. We know that the car is traveling at 15 meters per second, and we know that things that end in meters per second are representing velocity. Finally, we also see that the car tire radius is 0.300 meters. So if we look over here, let's see if we have an equation that relates these three or if we'll need to do additional work before selecting an equation. If you look closely, you should see up in this corner, I'll highlight it in yellow, we have an equation that says V equals R times omega. Well, that has all of the variables we need, so let's write it down. Let's rearrange this so it says omega equals. Plug in our values. And solve. And when you plug this into the calculator, you should find your answer is 50. And you're going to notice the unit meter. So the M cancels out, leaving you with what seems to be 1 over S. That is actually 50 radians per second. And this is going to be equal to omega. So the angular velocity is measured in radians per second and not meters per second. This is because it is traveling in a circle. It is just spinning around. Okay, that one was pretty straightforward, so let's take a look at a second one. In this second one, it's a bit more complicated, but not much more. We're going to be calculating the centripetal acceleration of a point that's 7.50 centimeters from the axis of an ultracentrifuge spinning at 7.5 times 10 to the fourth revolutions per minute. And then we'll determine the ratio of this acceleration that is due to gravity. Okay. Since we're just starting this unit, that might feel like an overwhelming question. You are not familiar with calculating values for objects moving in a circular motion, and it honestly requires you to think about it a little bit differently and to use an entirely new set of equations. But don't worry, you will become an expert. That's the goal. Before I get started, I already see an issue, and that is the fact that I'm given centimeters, which we know is never going to work. We always need meters, so let's just go ahead and convert that to meters. Now, in the previous problem, I mentioned that the value for angular velocity needs to be in radians per second. We don't have that. We actually have revolutions per minute, and that's a problem. So we're going to have to convert this first. This is our angular velocity, but let's convert that to radians per second. We do that like so. So times 10 to the fourth, and that's revolutions per 1 minute. The relationship between radians and revolutions, I will write it over here. 1 revolution equals 2 pi radian. You might remember that from a previous class, or you might not, and that's okay. So if revolutions is on the top here, let's write 1 revolution on the bottom, 2 pi radian on the top. We'll keep this going because we now have to convert meters into seconds, and that would be 1 minute. So I had minutes on the top. Now, I'm sorry, minutes was on the bottom. Now it's on the top to cancel it out. There are 60 seconds per minute. And we plug this in the calculator and find that we have 7853.98, and that's radians per second. All right, now we have our angular velocity ready to go. Since we are not looking for the same thing we were looking for in the first problem, instead it says calculate the centripetal acceleration. Centripetal acceleration is abbreviated as A with a subscript of C. And if you take a look at the equations, we see that in a couple of spots. We see it here and we see it again there. Considering the information we already have, which is angular velocity and radius, it makes more sense for us to choose this one. Centripetal acceleration equals radius times omega squared. We have those values in the correct units, so let's go ahead and plug in. 0.0750 meters, and that's 7853.98 radians per second squared. So by plugging this into the calculator, we can pretty quickly find that the centripetal acceleration is 4.63 times 10, to the 6th meters per second squared. Oh, not meters. Look at that. See, I did it too. Radians per second squared. Wow, that's a pretty fast acceleration. Around 4.5 million radians per second squared. And then it wants us to determine the ratio of this acceleration to that due to gravity. Ooh, okay. So for that part, we would just take our value, the one we just got, so 4.63 times 10 to the 6th. Remember, a ratio is like a fraction. Gravity is 9.8. You can already see that this is going to be a massive difference. You get approximately 472,449 times the acceleration due to gravity. That is a lot. Okay, there are the first two problems.